Well, thank you very much. So chaos theory, I'm going to assert, is really one of the great theories of 20th century physics. It essentially describes how relatively simple systems, I'll demonstrate two in a second, can exhibit extremely complex and unpredictable motions. So it tries to make sense of what is seemingly chaotic and complex from something at heart is simple. And that's really going to be the key message of my talk. But I've got a couple of demonstrations, and I'm very grateful to the Royal Institution staff for actually making these up. And they're both pendulums of a sort, pendula, I suppose. The first one is a pendulum which has two rather than just one pivot here. So you may have seen this, but it's quite a nice demonstration of the sort of complex. So if I start it here, it's kind of pretty much like an ordinary pendulum, just goes backwards and forwards in a predictable way. But if I start it a little bit higher up, you'll see the sort of very irregular, hopefully you'll see the very irregular kind of way in which the lower pendulum oscillates around. And it would be very hard to predict, for example, with a computer, how that lower pendulum, will it go around once more? Yes, just made it. The second one is another pendulum, but it's got some magnets underneath it. I'm going to use this a little bit later on in the talk for another purpose, but for the time being, let me just watch how the pendulum makes its kind of very irregular way. I hope you can sort of see that maybe. Makes its very irregular way around the magnets. And again, extremely hard to predict. Very kind of complicated trajectory, but very simple dynamics. This is a picture of me in my office with a couple of my group. This is kind of one of those time-lapsed photographs with a little LED at the end of the second magnet, and you can just see, how kind of complicated that looks. Okay. I'm going to focus on a particular chaotic model that was not a physical model, although actually you can make a physical model out of it, but it's really devised as a piece of mathematics. Don't worry, I've written some equations down, but you don't have to understand any of these equations except for one thing, which I'll tell you what that is in a minute. But these were equations discovered by the guy on the top left, Ed Lorenz, who was an American meteorologist who was actually trying to show a simple model of weather and why weather is so difficult to predict. Now, as I say, you don't need to know anything about these equations except that Lorenz made use of a mathematical discovery by Isaac Newton called the calculus, the so-called differential calculus. My point about saying that is that if one were able to kind of go back in time and show Newton the equations that Lorenz had discovered, Lorenz discovered them in the early 1960s. So if you went back 300 years and showed Newton those equations, he would have actually understood exactly what they were. He would have said, oh yeah, that's three coupled nonlinear differential equations. In other words, it's an equation, the little dot above the x, y, and the z on the left-hand side of the equation denotes what's called a time derivative, how fast these quantities are changing with time. But anyway, the point is that Lorenz made use of kind of classical mathematics to describe his equations. And yet, the equations generate a type of geometry that Newton would have been utterly alien to Newton. He would have had no concept whatsoever of the type of geometry that these equations generate. And that's what I want to talk about. So that's a picture of the geometry. But just to sort of say, what would Newton would have gone to school, and like all people at that age, indeed up to pretty much, when I was at school, you were taught about Euclid's geometry, the geometry of spheres and ellipses and ellipsoids and things like that. And the thing about a sphere is, if you kind of zoom into a sphere sufficiently, that was a bit of a tongue twister, it kind of gets boring. It just gets flat. It looks flat. It's just you kind of lose all of the structure, or an ellipsoid, or a hyperboloid, or any type of Euclidean geometry looks boring if you zoom into it enough. But these types of geometries, which we now call fractal geometries, never get boring. You can zoom in as much as you like. You can zoom and zoom and zoom and zoom, and you'll still see structure in this geometry. And what I'm going to argue in this talk is that this geometry provides a bridge between the classical, mathematical, and indeed physical world of Newton. Incidentally, Newton's great discovery that planets go around the sun on ellipses is a kind of an application of Euclidean geometric thinking. But these fractal geometries are a kind of a bridge between that classical world and, first of all, the world of 20th century mathematics. And the bottom here, I've got three of the greatest 20th century mathematicians, Kurt Gödel, Alan Turing, and Andrew Wiles. And I'll talk about them a little bit more. And I'm going to claim that this fractal geometry provides a link between the maths of Newton and some of the greatest discoveries in 20th century mathematics that these three individual mathematicians helped show. And I'm also going to claim, and this is my own personal view, that this type of geometry can also explain one of the most conceptually difficult experiments in 21st century physics. In fact, it was an experiment that was performed by three experimenters who won the Nobel Prize in 2022, what's called the Bell experiment. And the Bell is named after John Bell, Irish physicist, at the bottom of those three. And it seemed to resolve the big debate that Einstein and Bohr, Niels Bohr, had in the early 20th century in favor of Niels Bohr. And I'm going to claim that fractal geometry actually might tilt the balance back towards Einstein. That's my view. Not everyone necessarily agrees with me on this, I should say. Okay, so I'm actually going to claim chaos theory is actually one of the three great theories of 20th century physics: quantum mechanics and relativity. Einstein's special and general theory of relativity are clearly two mega theories in physics. I'm going to claim that chaos theory is the third. And not only that, at the end I will try to, as I say, make the claim that one of the holy grails of physics, which so far has eluded physics, and it's been a holy grail for at least 70, 80 years, is trying to marry quantum mechanics and general relativity theory together into a unified theory. We just don't seem to be able to do it. And my claim is that the geometry of chaos may be the missing ingredient here. Okay, so that's for later in the talk. So let's start by talking about these three great theorems of 20th century mathematics. So Kurt Gödel, a kind of mathematical logician, Austrian, in the 1930s, proved this kind of remarkable result, which is that the set of mathematical truths is actually much, much larger than the set of things that can be proven by algorithms. So algorithms are things that run on your computers in a kind of sequential way. We can prove certain things on computers and with algorithms. But Gödel said that mathematical truth is much, much bigger. What we can prove by algorithms is a small part. It's a very kind of esoteric result, but nevertheless kind of conceptually important. And Alan Turing, at sort of roughly the same time, in a sense, he came up with a specific example of what Gödel was talking about. And he took what is called Hilbert's decision problem. I'll explain what Hilbert's decision problem is in a second, but just it's a problem. And he showed that this problem posed by the mathematician David Hilbert some years earlier cannot be solved by any computer, no matter how powerful. In other words, it can't be solved by algorithm. One of the great, remarkable things about Turing's paper was that to prove this result, he had to define what a computer was. In those days, there weren't electronic computers. So he kind of devised what's now called a universal Turing machine, which is really what we now call a general-purpose computer. Andrew Wiles in the 1990s proved the very kind of famous conjecture. It's sometimes called Fermat's last theorem, but Fermat didn't actually prove it, but he conjectured it, that a certain equation, this equation, x to the n plus y to the n equals z to the n, has no solution in integers, whole numbers, positive whole numbers, if n, another whole number, is greater than 2. So 3 squared plus 4 squared equals 5 squared. That works when n is 2, but if n was 3 or 4 or 5 or anything greater, you can't find any kind of these whole number solutions where x to the n plus y to the n equals z to the n. And this has been kind of bugging mathematicians for centuries and centuries, and Andrew Wiles finally nailed it in the 1990s. So I want to describe why fractals say something which sort of sounds bizarre, perhaps at first sight, to these three great results. And to do that, I have to introduce you to the concept of state space. This is going to be an all-important concept. And to introduce the concept of state space, I'm going to imagine buying a pair of trousers. Substitute your own article of clothing or something if you prefer. So buy a pair of trousers. You have to decide, obviously, what leg length you are, what your waist size is, and maybe the trousers come in different colors. Call them shades of gray, if you like. So you have 3 parameters that you have to decide on if you want to buy a pair of trousers. Now, if you wanted to, you could imagine a pair of trousers being represented as a point in a 3-dimensional space, a kind of abstract 3-dimensional space, not physical space, but a sort of abstract space, where one dimension, the up dimension, represented the length of the trouser. So the longer the trouser you had, the further up that axis would be the point, and another axis would be the width of the trouser, and the third axis would be the grayness. And so a particular pair of trousers is represented by a point. So if you project the point onto the up axis, it gives you the length of the trousers. You project it onto the axis going into the page, it gives you the width. And if you project it down onto that horizontal axis, it gives you the grayness. So this is an all-important concept in this talk, state space. And it's the state of a pair of trousers, if you like. Now, you could imagine that, I don't know, there was another, perhaps you had another option before you bought your pair of trousers, which was how much, what ratio between, let's say, natural material and synthetic material, sort of, I don't know, cotton and polyester. You had an option of all cotton, all polyester, or some mixture in between. So then, if you wanted to represent a point in this extended state space, the state space would have to have a 4th axis, somehow orthogonal to these other ones. So you'd have to go into the 4th dimension. Now, the point I want to make is that I hope from a kind of concept, although we can't, none of us can imagine what 4 dimensions is like, but I hope from a conceptual point of view, saying that a pair of trousers where you have this additional dimension of material being a point in 4-dimensional space is not terribly conceptually, I mean, you can't visualize it, but conceptually it's okay. Because what I want to talk about later on is kind of potentially enormously large dimensional state spaces of the whole universe, actually. And if you get confused, just think trousers with a few extra, then you'll be good to go. You'll be a cosmologist.